separate. So this is the one that characterizes the best hyperplane that separates them. But if we can relax this condition a little bit by saying, well, I don't necessarily need it to be bigger than or equal to 1. I just need it to be bigger than or equal to 1 minus some positive term, so some small positive term. So subtract something from the 1 here. It's easier to satisfy this condition here. So I'm introduced some new parameters, ci bigger than or equal to 0, and I relax my condition to be that this dot product, this expression here, is bigger than or equal to not 1, but 1 minus ci. So 1 minus ci is a slightly smaller number, so it's a little bit easier to satisfy this inequality here. So if I put this in, well, I don't want the CIs to become arbitrarily large. So if I take very large CIs here, well, then this condition here just becomes empty, right? I can just take CI so big that this is almost minus infinity, and then this condition here is still always positive. So so it'll be vacuous. It'll be.
Do we want to enforce that epsilon I should be less than 1? Otherwise, the vector and the yi will be in opposite direction.
CI.
Yeah, CI has to be less than 1.
No, we don't assume that. But if we make it bigger than 1, then this condition here is clearly satisfied. So we still want to limit CI somehow. We don't want to make it. We don't want to make the CIs too large so that they I mean, we still want some condition that the data points are further away from the line or from the hyperplane. So we don't want the CIs to become arbitrarily large. So instead of just minimize the norm of W, we make a regularization term here, which is we take the norm of W plus a constant C times the sum of these CIs here. You can see when we minimize this, right, then we also keep this term here not too large. So we can sort of play off the norm of W against the sum of these CIs here. So if we make C very, very large, take C very large, well, that means that in order to minimize, we have to make the CIs very, very small. And so that means that this condition here is almost satisfied. It's very close to being satisfied. The CIs have to be very small. If on the other hand, C is a small number, then then the CIs can be larger and still have a minimum. So the new minimization problem is minimize this again subject to these conditions here, and that's also a convex problem that can be again formulated in terms of alpha. So we can take the dual problem, which turns it into a problem of maximizing. So the minimization problem turns into a maximization problem. That becomes very simple. Becomes a problem of finding the alphas, again, the maxima. So I guess it should have been a plus. I wrote a minus on the board, so that was a mistake. So the sum of the alpha i's plus half of these things we have here, subject to, again, the sum of the yi times alpha I are 0. The alpha i's have to be positive. And again, W is then equal to yi alpha I xi. I also made a mistake when I wrote this. But now the condition is not just that alpha I is bigger than or equal to 0, but that alpha I is less than or equal to this constant C. So this problem here, minimizing this problem here, minimizing this expression here under these constraints, becomes a problem of finding these alphas that maximizes this condition, satisfies this condition, and now satisfies not just that they're bigger than or equal to 0, but also that they're smaller than or equal to C. And so this problem, which seems to be somewhat more intractable, it turns out to be in the dual formulation here, it turns out to be very, very simple. It just introduces this other constraint here that the alpha i's can't exceed C. And again, the W that we're looking for just becomes this linear combination of the of all the data vectors. And again, the alpha I is here only going to be non-zero when xi is a support vector. So that relaxes the requirement that we can separate them linearly, but it does not mean that we can solve any problem here. So if we look at a data set that looks like this here, so here we have two types. We have the crosses, say they're -1, have label -1, and the dots here outside have a label +1, but it's very clear that there's no possible way that we can linearly separate those in R2. There's no line that can separate all these points here. That's impossible. So and we could try to solve this by introducing these CIs. They're called slack variables because they sort of slack the problem a little bit. They make the problem a little less exact. They put a little slack in the problem. So there's no way we can do this, and we can separate these. But now the interesting idea is that suppose we map these points into R3, and we map them by this map here. It's a map from R2 into R3 that takes a point x1, x1, x2, and it sends it to the point x1, x2, and then the norm squared of this vector, or the distance from the origin. So what does that look like? Well, that sort of takes the plane in the R2 plane, and it folds it around this paraboloid here. And so this is a surface in R3 where you cut it. It's a parabola. So this maps R2 into R3. And what happens to our data set here? Well, our data set here, we have these points here that are inside the circle here. The points that are inside the circle, right, they have distance from the origin less than the radius of the circle. Right. Those that are outside, they have radius bigger. Or they have distance bigger than the radius. So what happens is that those that are inside the circle, they will, their z coordinate, the coordinate in this direction here, will be smaller than the radius of the circle. And those that lie outside the circle, they'll map to points whose z coordinate is bigger than the radius of the circle. And that means you can separate the data set now in R3 just by looking at the hyperplane that goes through that z equal to r. So there you'll have the points that were outside the circle, they will be above this, and the points that are below this that were inside the circle will be below this hyperplane. So there you have a hyperplane that separates these two data sets. So the idea here is that by mapping the data set into a higher dimensional space, or in this case into R3, then you can solve the problem in the bigger space. And that turns out to be good enough. So in general, if we have a data set in Rn, say, so we have xi's, data vectors in Rn, and we have labels yi plus minus 1, then we can try to find a map into a bigger space such that in this bigger space, the transformed data set is separable, so that the points with the same labels, but where we map them into a bigger set, that they can be separated. So this turns out to be a really great idea, and that it works fantastically well.
So here, when you are mapping to the different space, the dimension of, we just need one more dimension, or the m has to be
No, you might need many more dimensions.
Many? Okay, so it was just for that two-dimensional case.
Yeah, this was just for this example here, right? This is just for this example here. In general, you can need many more.
Okay.
But the thing that we'll get to, the thing that makes this, yeah, go ahead.
Do we have any kind of bound on what how much larger M must be, Niels?
No, it can be infinite dimensional, as a matter of fact.
But that means your data set is horrendously.
Yeah, that's what one would think, but as it turns out, it's not so bad. I'll show you why it's not so bad. It turns out that, yeah, even though if you map it into an infinite dimensional vector space, where you can't really do computations, it is not too difficult to, you can in fact still solve the problem. So the idea is that if we look at the maximization problem, the dual maximization problem, right? What we had over here was the, I wish my pen would work.
So it looks identical to the previous one, except there is a coordinate transformation in between.
Yeah, that's right. You have the phi xi dot phi xj, right?
Yeah.
You can see that.
Yeah.
But that's all we need. We only need the dot product. If we look at the conditions, find W, right? W will be a vector in the bigger space, because there was a linear combination of the data points. So this now will be this linear combination of the transformed data points. So W will be a vector in the big space. But what is it we need in order to classify a new point? We're going to get a new point in Rn, and we want to classify that. So what we have to do is, well, we have to take and look at which side of the hyperplane it lies, right? And that means we have to dot it with, we have to map it into the big space, dotted with W at this this B here, this what we call, maybe call it minus C prime before, and see if that's positive or negative. That'll determine the sign of the label. But again, let's look at what happens. How do we compute this? It's W dot phi of x, so that's a dot product in the big space. But if we look at what it is, it's yi alpha I phi xi, that's W. And then we dot this with phi of x. Again, what we find is that all we need to do is to know the dot product phi xi dot phi of x. So we don't actually need to know what these vectors themselves are. We just need to know what the dot product is. Same thing up here. All we need is the dot product. And this is the really great discovery that makes all this possible. There's a so-called kernel trick, because we only need to know the dot product. We don't need to know exactly what this phi is. And so the
and here we can make an ansatz for phi. We don't have to optimize on phi or anything, but as long as there's a hyperplane, we're done.
Yeah, well, yeah, that's fine. If we can find a hyperplane, we're done. That's fine. But we don't need to well,
the best phi or the best M or anything.
No, we don't care about the best phi. That doesn't matter. I mean, if you have any phi such that we can solve it up in RM, then we're happy.
But I think we still need to find that RM of phi where it's a hyperplane which is separating the data points.
Yeah, that's right.
That's the only condition.
But I think the comment I made, Manish, was that if you make a guess for phi and M, and as long as you luckily find a hyperplane that works, you're done.
Correct.
I don't need to find the best value of M or the best value of phi.
No,
I could just pick my favorite phi.
I think whatever rates will work, I guess.
Yeah.
But I'll say it's not so easy to guess a phi.
No, I know. I'm curious about all the quote-unquote goodness properties of these things, right?
Yeah,
what is a nice phi? What is a nice...
But as I said, the thing, it turns out you don't really need phi. What you do need is a way to take the dot product between two transformed vectors.
Yeah.
And if you think about that, what is that? Well, that's a function of two vectors in Rn. So you take two vectors in Rn, xi and xj, map them up by phi, and then take the dot product. So that's a function of two variables in Rn. So it takes two vectors in Rn and maps it to a real number. And so that's what we're going to look at. Instead of looking at phi, we're going to look at this map, which takes two vectors, map them up to Rm, and take the dot product up there. That's a function from Rn cross Rn into R, which is given by this dot product here, right? So that's fine. But the thing that's interesting is that if we have such a function, k is this function here satisfying certain conditions, then in fact there is a phi. We don't know. It's the proof is not something that constructs phi. That's. I mean, you can.
It's an existence result.
Yeah, it is. I mean, you can compute it, but it's a complete mess. It's not something you use for anything. But these functions, k here, they're known as kernel functions. And so, if you have such a kernel,
is there an intuitive way to see that computing or defining a kernel is easier than constructing the lifting coordinate transformation?
Yeah, absolutely. I can construct you 1,000 different kernels. It's very easy to construct kernels. It's very difficult to construct these feature functions, the phis, so the ones that map into Rn. They're very difficult to construct. But kernels are a dime a dozen. There are lots and lots of kernels.
Because they have this separable criteria. They seem to split into a product of two functions, right?
Well, I mean, that's the theorem is that you can split it into, if it satisfies these certain conditions, then you can split it into a product of these two of the feature function. Then it is of this form. That's a theorem. That's not an easy theorem to prove, but it can be shown. But there are lots of kernels, and let's see an example of such a thing. So a function, such a function, capital K, is called a Mercer kernel, and the optimization problem now becomes maximizing this expression here. So now you can see that the dot product phi of xi dot phi of xj has been replaced by the value of the kernel function. So if you have a kernel and you know how to compute this kernel, then you just plug that in instead of the dot products. And then you try to optimize this expression here. These are just certain numbers here. And you try to solve this this maximization problem. And then again, the function that you need in order to classify points, again, it's just given by this expression here. You see now the dot product phi xi dot phi x is replaced by k xi comma x. So once you know the kernel function, you don't need to know phi. You can solve your problem. You can at least formulate the optimization problem, and you can also once you have solved this, you can classify new data points, and so the problem is solved in that case. So let's try let's try an example here of a. So I think Chidi has tried to solve this, right? Isn't that the one I put this on the homework, and there's no solution to it. So you're trying to find the either logistic regression or support vector, linear support vector machine that separates these points here. So this is known as this is the negative XOR. So if you have value, so you have a truth value. If they're different, you get it's false, and if they're equal, it's true. So this is a problem that is not linearly solvable, and you can't in fact, if you try to do either the try to do a support vector machine, linear support vector machine, even with the slack variables, you can't solve it. You're not going to get a solution. So let's see that we can solve this by using a kernel. So well, if we try to solve the optimization problem without using a kernel, we only get the solution that all the alphas are 0, and that of course that's not a solution because it doesn't define a line. But let's try a kernel function now. Let's try a kernel function R2 cross R2 into R, which is very simple. It takes the dot product of the two vectors and squares it. So instead of just taking the dot product, which would be the original problem, we take the dot product and we square it. So this is in fact a kernel function. And in this case, one can in fact find the feature function. That's a function from R2 into R4, which is defined in this way here. It takes squares the first coordinate, and then second coordinate is the product of the two coordinates. The third one is also the product of the two coordinates. The fourth one is the square of the last coordinate. So that's a feature function from R2 into R4. And if you try to take 2 points and map them up to R4 and take their dot product up there, you'll find that that dot product in R4 is precisely the square of that dot product in R2. So there we have an example of a kernel. The feature function is given here. And you can see the kernel function is very simple. It's just taking the dot product and squaring it. And let's try to see what happens if we now use this this kernel function here and try to look at our problem. So if we take these 4 points in R2 and transform them up to R4, we get these 4 points here. So these are 4 points in R4. And the constraint optimization problem is given by this. See here again, kxi comma xj is just the dot product squared. And if you write all this stuff out and tries to solve this subject to this condition here, alpha 0 minus alpha 1 plus alpha 2 minus alpha 3 is 0. And 0 less than or equal to alpha I less than or equal to c. C is some constant that we can choose. So if you try to solve this problem, it turns out that you can in fact solve it. So
sorry, I missed it. Like, how did we get like the those points in R4 as 0, 0, 0 and 1, 0, 0, and there was
you just map them by this function here, right? So let's see, we had the point, the 0, comma 0, right? So that obviously goes to 0, comma 0, comma 0, comma 0, right?
Okay.
And then we had the point 1, comma 0. That goes to 1.
Oh, okay. Using this function.
0, 0, 0, and then yeah. So it's just mapping the 4 points using this map here. So mapping it from R2 to R4. So yeah, so we can go through the whole thing here and try to maximize this using this constraint here to express alpha 3 in terms of alpha 0, alpha 1, alpha 2, and then try to differentiate and blah, 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 and solving this. We get, in fact, a solution. And we get the solution. Alpha 0 is 4, alpha 1 is 2, alpha 2 is 4, and alpha 3 is 0. So if we take a constant big enough that we could take c equal to 5, we could take c equal to 7, or whatever, anything bigger than equal to 4 will work. Then we have the constraints satisfied, and so that means we get a solution. And so the W we get is a vector in R4, right? That's And if I write it out here, I get I have found my alphas. I have my 4 data points here. I can compute it, and I get that W is the vector 2, comma minus 2, comma minus 2, comma 2. So that's a vector in R4. And so I can dot that with vectors from R2. I can take a vector in R2, map it up to, we should also find B, as you said, we find, in fact, get B equal to minus 1. So if we go up to R4, then the hyperplane that separates these 4 points in R4 is given by this equation here, 2x1 minus 2x2 minus 2x3 plus 2x4 minus 1 equal to 0. So that's a hyperplane that separates these points in R4. But we can't draw that. We can't see what that is, because we can't draw 4-dimensional pictures. So, but we can try to see what does it correspond to in R2. So we can take the map. We can take the points in R2 that map to this H. So that means we take all the points in R2 such that when we apply phi to it, we land in H. So there will be some configuration of points in R2. And you can, in fact, solve this again. You have points x1, comma x2 in R2, such that when you dot it with this vector W, you get 1. And if you write this out in terms of x1 and x2, you get 2x x1 and x2, you get 2x1 squared minus 4x1 x2 plus 2x2 squared equal to 1. So that's just, well, if you recognize this is divided through by 2, and you find that this is the configuration. There's a set of points x1, comma x2 and R2, which has the property that the difference, the square of the difference, is equal to a half. So this is pretty easy to see what that is, because you can just factor this out. So this is this means that x1 minus x2 is equal to plus minus 1 over the square root of 2, and so that gives you 2 lines. You get this line and this line. So the set that separates these points in R2 is not a line, it's 2 lines. And here it is. These are the 2 lines that separate these points in these 4 points in R2. You can see it separates the plus one label plus 1. That will be inside between these 2 lines, and the minus 1 will be outside. So we get a not a line separating. We're getting it, and this is a quadratic. It doesn't look like quadratic, but it's 2 lines. 2 lines is quadratic. So it is a quadratic curve in R2 that separates these. So by using this kernel trick here, we were in fact equal to find a curve that separates these points, not linearly, but a quadratic curve that separates them. So this can be generalized. We can use all kinds of strange kernel functions. Here's one that is what is the RBF function. This is a radial basis function. So this is a kernel function. This is say sigma squared times the exponential function of the square of the difference between the 2 vectors divided by some 2L squared. This is sigma squared is known as the variance. This is called the length scale, and L squared is a length scale. So this is the kernel function, but that corresponds to that in fact corresponds to a feature function that maps into an infinite dimensional vector space. So we don't want to deal with taking looking at vectors with infinitely many coordinates. But we don't have to, because all we need to do is to know what their dot product is in this infinite dimensional space. And the dot product of these two, of when you lift them or map them up to this big space, is just given by this function here. That's all we need, because that's all we need for the to solve the problem. And so that makes it possible to, if you remember some of the separators that we looked at in the beginning of this section here, where you're trying to, let me go back and find it.
What is SVC? SVM was support vector machine. What is C stands for?
Classifier.
Classifier.
Support vector classifier. So we were looking at this data set here. And this is just clearly not linearly separable. And we tried different. Here's a linear SVM. Here's this is in fact a support vector machine where we use this kernel, this RBF kernel, radial basis function kernel, and so that gives a somewhat better separation by if you adjust these hyperparameters, this length scale and the variance, you can get it to separate pretty well. So let's go over and look at some code and try this data set of this credit data. So let me go over to the I just need to start my Jupyter notebook. Okay, let me share the code again.